Let's talk about logarithmic functions and their graphs. Earlier, we talked about functions that pass the horizontal line test, and if that's true, then they're one-to-one functions, and therefore they have an inverse function. Well, exponential functions pass the horizontal line test, which means that they too must have an inverse function. These functions are called logarithmic functions. So let's define that a little bit. For x is greater than 0, a is greater than 0, and a cannot be 1, y equals log base a of x if and only if x equals a to the y. The function given by f of x equals log base a of x we read as, well, log base a of x. This is the logarithmic function with base a. Now, what's interesting here is that this logarithmic function, y equals log base a of x, if and only if x equals a to the y. So that means that we can actually translate a logarithmic function into an exponential function, as well as an exponential function back to a logarithmic function if we really wanted to. That's going to be helpful for solving some different problems that we've got. As an example, let's take a look at these four here. I want to evaluate the following. F of x equals log base 2 of 32. Well, I don't really have a way to answer that as it is, and when I look at my calculator, I've got some log buttons on my calculator, but these are really log base 10. We're going to learn more about what that means later on. I've also got a natural log button on my calculator, again, something that we're going to learn about in a little bit. So what I'm going to do instead of using my calculator is I'm just going to translate this from a logarithmic function to something with an exponent. Okay, so I've got y equals log base a of x and x equals a to the y. These two are equivalent. So then if this f of x, which is just fancy for y, is equal to log base 2 of 32, then I can actually change this to say the base of this logarithm is going to be the base of this exponential equation here. So I'll put 2 to the y, so I don't know what that is equal to x is 32. Okay, so then this is really asking 2 to what power equals 32? 2 to what power equals 32? Well, that's 5. 2 to the 5th power equals 32. Therefore, y equals 5. I just evaluated what log base 2 of 32 is. This one, f of x, again, fancy for y, equals log base 3 of 1. I can change this to say the base of this logarithm is the base of this exponent, and I can say 3 to the unknown y is equal to 1. Well, 3 to what power equals 1? 3 to 0, because anything to the power of 0 equals 1. Y equals 0. I just evaluated what log base 3 of 1 is. Okay, another one, log base 4 of 2. The base of this logarithm is the base of this exponent, so 4 to the y is equal to 2. 4 to what power equals 2? Well, I know the square root of 4 is 2. Therefore, 4 to the 1/2, y equals 1/2. Last one here, log base 10 of 1/100th. All right, so let's change this up. The base of this logarithm is the base of this exponent, so then 10 to the y is equal to 1/100. All right, I know 10 to the 2nd power is going to be just 100, but I don't want 100, I want 1/100th. So if 10 to the 2nd power is 100, then 10 to the -2 is going to be 1/100. So this is one case where just translating from one to another, logarithm to exponents, is helpful. Okay, let's take a look at some properties. The logarithmic function with base 10 is called the common logarithmic function. It's common because it's found on a lot of calculators. It's used quite often. It's something that we can actually calculate with some technology. The properties of logarithms listed below follow directly from the definition of the logarithmic function with base a. Okay, so I've got some properties here. Property 1, log base a of 1 equals 0. Well, we saw an example of that because a to the 0, anything to the 0, is equal to 1. Okay? Log base a of a equals 1. All right, well, this means that a to the first power, remember we can translate this to exponential equation, a to the first power equals a. So if you've ever got a base and what you're taking the logarithm of, if they're the same, then that's just going to be 1. If you've got any base and you're taking the logarithm of 1, that's going to be 0. So those two seem to be important to remember. And here I've got, this is called an inverse property, log base a of this whole thing, a to the x, is equal to x. And that's because a to the log base a of x is equal to x. So essentially, this log base a and this base of this exponent a, these will undo each other. Same with up here, a and then the log base a. These are going to undo each other, leaving just whatever this x is. And then lastly, if log base a of x is equal to log base a of y, then x equals y. Well, that makes sense. If I'm taking the logarithm of something and I'm saying it's equal to the logarithm of this other thing and they're of the same base, then I can just cross those out and say x equals y. Okay, so let's take a look at some of these examples and try to figure them out based on these properties. I've got, for e, log base 2 of x equals log base 2 of 3, solving for x. Well, this is log base 2, and this is log base 2. So I can essentially say, based on this property right here, property 4, my 1-to-1 property, I can go this log base 2 and this log base 2. Okay, those will undo each other, leaving just x equals 3. And this is by this 1-to-1 property. Okay, f, log base 4 of 4 equals x, solve for x. I see property 2 here says log base a of a. Okay, log base a of a equals 1 because a to the first power equals a. So since this base is the same as what I'm taking the logarithm of, then this is just going to be x equals 1 by property 2. All right, these next two, I want to simplify these. Log base 5 of this whole thing, 5 to the x. Now that looks similar to my inverse property up here, property 3. It says log base a of a to the x equals x. So my log base a and my a here undo each other, which means down here, my log base 5 and this 5. Okay, undo each other, leaving just x. And what about here? 7 to the log base 7 of 14. This again looks like my inverse property, except it's this one over here, a to the log base a of x equals x. So the a and the log base a, 7 and the log base 7, those will undo each other, leaving just whatever was this x here, in this case, 14. Okay. Well, that's how we're going to use some of these properties to solve for x as well as to simplify. Let's next take a look at some graphs. I've got here, as I mentioned, an exponential function as well as the inverse of this, which is a logarithmic function. So my exponential function is f of x equals 2 to the power of x. And the inverse of this is going to be g of x equals log base 2 of x. Well, I've plotted some points here, as we see in the table, and I've also put this horizontal line y equals x to show you that indeed these two are inverses of each other. Okay, so I see a lot of these points, okay, they're going to get closer to this y equals x, they get further away, and just like a mirror, this log base 2 of x, they'll get a little bit closer to this f of x symmetrically, and then they'll also get further. All right, when we were talking about exponential functions, we also talked about e, the natural number. And, well, that's going to come into play here as well. The function f of x equals e to the x is also one-to-one, and as such, it too has an inverse function. We're going to call this the natural logarithmic function. Defining that a little bit, for x is greater than 0, y equals, here this is ln, we're going to say this is the natural log of x. Y equals the natural log of x if and only if x equals e to the y. So again, we are able to translate this one to another from the natural log function to something with e to the y here. Now that's because technically the natural log of x, it isn't shown here, but this is the same as, right here, log base e of x. So this is called the natural logarithmic function. So we're going to evaluate a few things here as well. The equations y equals the natural log of x and x equals e to the y are equivalent. What we're going to do is we're going to evaluate these things, the natural log of 2, the natural log of 0.3, the natural log of -1, and the natural log of 1 plus the square root of 2. Okay, now, in this case, these natural logs are things that we can put into our calculator. So let's bring up a calculator. Let's just start by plugging in what is the natural log of 2. And the nice part about Desmos here is you can just type in ln, and it will recognize that you mean the natural log. So we're going to put in the natural log of 2 here. Okay, and so that appears to be 0.693. Okay, what about the natural log of 0.3? So again, I'm just going to plug in ln and then 0.3. This is negative 1.204. We'll round that up because of the 9 there. The natural log of -1. Natural log of -1. Ooh, it's undefined. We'll talk about more of that later on, why that is. And then the natural log of 1 plus the square root of 2. 1 plus, here we'll do the square root of 2. Is 0.881. Okay, let me bring this over to the side and I'll write those answers down. So this first one was 0.693. The second one was negative 1.204. This third one, the natural log of -1, was undefined. So we'll say that it gave us an error or it's undefined. We'll talk more about what that means later on. And then 0.881 was this last one here. And just like other logarithmic functions, we also have properties of natural logarithms. Now you'll notice these look very, very familiar. The natural log of 1 equals 0. That's because e to the 0 equals 1. Very similar to my other properties. The natural log of e equals 1. Well, that's because we've got technically a log base e, then I'm taking of e, So e to the first power equals e. And the natural log of e to the x equals x. And e to the natural log of x equals x. My inverse property, similar to the other ones. And my one-to-one property, if the natural log of x equals the natural log of y, then x equals. So let's get a real-world application to finish off this lesson. Students participating in a psychology experiment attended several lectures on a subject and were given an exam. So much like you, these students were taking a class, they learned some things, and then at the end of the unit, they took an exam, they took a test. And in this case, though, every month for a year after the exam, the students were retested to see how much of the material they remembered. So they learned something, they took a test, that was kind of like their baseline, if you will, and then every month after that, they took a very similar test to just kind of gauge how much were they able to recall. Okay, so how much of this were they able to remember? Well, the average scores for the group are given by the human memory model. So I've got a graph of that here. And I can create a function based on this curve here, and this says f of t equals 75 minus 6 times the natural log of t plus 1, where 0 is less than or equal to t, less than or equal to 12, because this is talking about 0 months after the first one to 12 months after the first test. So t is the time in months, and we're going to answer a few questions here. What was the average score on the original exam? T equals 0 because 0 months have passed. So I'm going to grab my calculator again. Let's clear all these. And I can just go ahead and plug this in. I can say 75 minus 6 times the natural log of t plus 1. In this case, t equals 0. This is 0 plus 1. So the average score for the original exam was 75%. So let's write that down, 75. Okay, what about after 2 months? So this is after 2 months, they were tested again here, and let's find out how much of this did they remember. What would their score be then? I can just copy this. Let's paste this here and change the 0 to a 2. So now the average score went down, which kind of makes sense. We kind of forget a little bit about what we learned over time. And this shows that after 2 months, scores went from a 75 down to a 68.41, around that, 68.41. All right, what about 6 months later? So half a year later, they were tested again. How did they do this time? 63.32. So the average score there was a 63.32%. All right, so let's draw some conclusions here. Over time, the scores do go down. 75 to 68.41 to 63.32. And I can see that in our graph as well. We start out at 75 and we start going down following this curve here, which is a logarithmic function. Now, what I also notice is that it's a little bit steeper toward the first couple of months, and then not quite as much as we get further along. So I'm going to guess that this shows to 12 months, it's right around 60%. But if I were to go another 12 months, it probably wouldn't be that much lower than this. Like the biggest drop was in the first, 3 or 4 months here. And so we'll be solving problems like this in our assignment and doing a lot more with logarithms and exponential functions.